My name is Amit Kumar. I am postdoc researcher. Okay. Okay. So, hello everyone. My name is Amit Kumar. I'm a postdoc researcher at Clean Water Technology Lab, Helmholtz Research Institute, Dresden, Germany. So, in the beginning, first I would like to talk about my research institute and research group. So, next slide, please. So, there are total 18 Helmholtz Research Institute in Germany. So currently I'm working at Helmholtz Research Institute, which is located in Dresden, near Berlin. So next slide, please. So I'm working at Clean Water Technology Lab, which is like a CLEWATEC Innovation Lab, a group of efficient wastewater treatment. It is an interface between research and industry. Like we are working with various industrial partners. Next slide, please. So we are working in 4 different research areas, like in wastewater treatment, related to wastewater treatment. So advanced oxidation process, for example, to remove emerging contaminants, and then efficient injection of oxygen for aerobic digestion. And then we are using various sensors for process characterization in wastewater treatment plants. And then energy sector, utilization of biogas to generate energy that can be utilized for wastewater treatment in wastewater treatment plants. Okay, next slide, please. Yeah. So, as we know, like organic micropollutants. Okay, my area of expertise are in advanced oxidation process. From here on, I will talk about AOPs. So, organic micropollutants are the group of like emerging pollutants that have been frequently observed in water bodies, and they are negatively impacting on our environment. So OMPs are like there are many sources of OMPs in water bodies, and for example through the direct discharge as well as from the wastewater treatment plants. So due to chemical complexity and stability of most of organic micropollutants, the conventional existing wastewater treatment plants are not capable to remove like most of emerging contaminants. So therefore, next slide, please. So therefore, people are working on advanced oxidation processes. So the main aim of AOPs is to generate hydroxyl radicals. There are many AOPs. And the hydroxyl radical is like having higher oxidation potential. It is non-selective, which can react with most of organic micropollutants. So next slide, please. So in my research, I'm using cavitation-based AOP, which is like a chemical and catalyst-free approach to oxidize various organic micropollutants. So the hydrodynamic cavitation is a like physical process that includes formation, growth, and implosion of bubbles due to huge pressure difference in the liquid. So when the due to implosion of bubbles inside liquid, it can generate, it can enhance the local temperature and pressure. That the local temperature and pressure can be very, very high. That can cause the generation of various radicals, reactive species inside liquid, and they can participate in oxidation of pollutants. So next slide, please. So we combine hydrodynamic cavitation with ozone to enhance the radical production. For example, hydroxyl radical and atomic oxygen, so that we can enhance the removal rate of particular pollutants. So next slide, please. So here is the experimental setup of hydrodynamic cavitation combination with ozone. So here we can here we can see that. So first we are preparing like how to say ozone solution. We were mixing with the pollutants. Then we were injecting to the cavitation chamber with by using high pressure pump. And then the main feed was the solution from the main line was passing through in the chamber in current direction, in co-current way. So I will show you in the next slide. Next slide, please. So here we can see the hydrodynamic cavitation chamber. So there is a nozzle. There is 4 mm inner and 6 mm outer die of SS steel, stainless steel nozzle, and having 300 micrometer orifice at the top. So the the pressurized ozone and pollutant containing solution was injected through this orifice, and the pollutant containing main line, the pollutant containing solution was injected in the chamber in co-current flow. So the next slide, please. Yeah. So we have conducted the experiments with various experimental parameters. For example, we varied nozzle pressure, different ozone doses, and yeah. So and we selected we have chosen succinic acid as an emerging pollutant. It is highly reactive with OH. It is selective pollutant. It is highly reactive with OS radicals, and it is not reactive with ozone. It is reactive but very slow with ozone. So it can provide the hydrogen yield during the cavitation process. So next slide, please. So here are some experimental results. In the first graph, I plotted the effect of nozzle pressure on the removal of that compound. And it was found that as the nozzle pressure was increasing, like the removal rate was increased. So there was like about 42% removal was observed at 40 bar of nozzle pressure and at low ozone doses. And there was no significant removal was observed when we have not added ozone in the solution. So in the second graph that I plotted, sorry, the previous slide. Yeah. In the second graph that I indicated that the effect of ozone doses, for example, the amount of ozone supplied to per milligram of pollutant. So it was found that when there was less ozone doses, like in the contactor, there was efficient removal. So when the concentration of ozone was increasing, there was it was playing a negative role on pollutant removal. So maybe due to the degassing and maybe some radicals were quenching in presence of high amount of ozone in the chamber, or maybe there was a lack of implosion of bubbles due to a high amount of gases inside the chamber. So next slide, please. Yeah, yeah. So as we knew the nozzle pressure and the flow rate at nozzle, we calculated the hydraulic power, which to calculate the energy yield. So for example, we spent about 20 watts of power in order to remove 42% of removal at low ozone doses. And based on that power, we calculated the energy consumption, and we found that there was less than 1 kilowatt hour per meter cube of energy consumption. That was comparable with existing AOPs, advanced oxygen processes, because they are consuming more than 1 kilowatt, more than 5 kilowatt hour power per meter cube of wastewater. So yeah, so that value was comparable, and we are trying to reduce, since we are treating 10 to 100 liters per hour wastewater. Next slide, please. So we have also treated some PFOS and PFOA fluorine-based compounds containing wastewater effluents. So as we know that fluorine-based compounds are like highly stable. I mean, they are stable due to like chlorine and fluorine bond, and they are less reactive with even though with strong oxidants like atomic oxygen and hydroxyl radicals. Uh, so we try to remove with hydrodynamic cavitation in combination with ozone, and we found like about 48% removal at the optimal conditions. So as I mentioned that like these compounds are less reactive with even the OH radicals. So as I mentioned in the beginning, like due to implosion of bubbles that creates like various chemical and physical effects. So these compounds can be degraded like with some radicals, as well as due to implosion of bubbles that like through pyrolysis, yeah, thermal degradation of these compounds. Yeah, next slide, please. Yeah, so it's time to summarize and conclude my presentation. So we are using hydrodynamic cavitation combination with oxidant.
Discuss this at ease.
Okay.
I won't rush you.
Okay.
It's very important.
Okay. Okay. So we are using hydrodynamic cavitation with combination of oxidants such as ozone to remove emerging contaminants. So far, we treated some PFAS compounds, a fluorine-based compound, and some industrial chemicals. And the presence of ozone can enhance the radical production and the removal rate of OMPs. And we have tested with several experimental parameters, for example, nozzle pressure and various ozone doses. And we found that higher pressure and low ozone doses were playing important role for the pollutant removal. And so far we obtained like more than 40% of removal at optimal conditions. And we spend like less than 1 kWh per meter cube of energy. So these data, like these numbers, give the hope for scaling of the device for large scale of wastewater treatment. Yeah. So next slide. Yeah. Thanks a lot for your attention. Yeah.